So we completed the magnetic circuits. Now we see the interaction effects of the magnetic circuits and the electrical energy. Now see the that is called electromagnetic induction. So the electromagnetic induction, so initially is found by Ørsted in 1824. He discovered a current carrying conductor having the magnetic properties. So that is, the magnetic field exists around the current carrying conductor. And then in 1831, the Faraday discovered when the magnetic flux linking a conductor changes, an EMF induced in the conductor. So this is the Faraday's laws of electromagnetic induction. Now we see the current carrying conductor in magnetic field. So this assume this is the magnetic field and this is the current carrying conductor. So the force acting on the conductor we define, that is F, that is equal to BIL Newton. So the B is equal to flux density of the medium and I is the current passing through the conductor and L is the length of the conductor. If here the assumption is the flux, that is the magnetic field is a right angle to the electrical field, that is the conductor is right angle to the magnetic field. So we get F is equal to BIL Newton. If the conductor is inclined at an angle theta to the magnetic field, like this is a magnetic flux, now the conductor is inclined to the angle theta in the sense, then the force F, that is equal to BIL sin theta. That means the force is reduced by the amount of sin theta and the direction of the force or the direction of the conductor is obtained by the Fleming left hand rule. So next we see the Fleming left hand rule. So Fleming left hand rule, if we stretch the fingers, that is middle finger and forefinger, thumb, the three fingers are a right angle to the each other. Now the forefinger represent the magnetic field and the middle finger represent the flow of the current and thumb finger represent the motion of the conductor. This is the Fleming left hand rule. So the force of the direction or the motion of the conductor direction is identified by the Fleming left hand rule. So next one is Faraday's law. So Faraday's first law is the same as the discussed in first. Whenever the magnetic flux linking conductor changes, an EMF induced in that conductor. And the second point is the magnitude of the EMF is proportional to the rate of change of flux linkages. And Lenz's law. Lenz's law is described. So whenever the EMF is induced in that conductor in such direction so as to oppose the cause producing it. So as per Lenz's law, the induced EMF always having the direction of the opposite to the applied source voltage or applied source current direction. So from that we can write the magnitude of average induced EMF, that is E equal to N phi 2, that is a final flux linkages, minus N phi 1, that is initial flux linkages with respect to time. So we can commonly, this number of turns is a constant, so we take outside, so N into phi 2 minus phi 1 divided by del t, that is change of time. So we can write in differential equation format, that is E is equal to N into d phi by dt. So the rate of change of flux linkages multiplied by number of turns. So now we incorporate here the Lenz's law. As per Lenz's law, that is the induced EMF always opposite to the opposite direction of the supply voltage. So induced EMF V, that is equal to minus N into d phi by dt. Then the induced EMF direction is find out by Fleming right hand rule. So in the same left hand rule, like if we stretch your right hand, forefinger, middle finger and thumb right angles to the each other. Now the forefinger represent the magnetic field and thumb represent the motion of the conductor and the middle finger represents the EMF induced in that conductor. So this is the Fleming right hand rule. So Fleming right hand rule is used in these generators, and the Fleming left hand rule used in this motor, because in motor the electrical energy converted into mechanical. So we find the direction of the conductor, so we apply the Fleming left hand rule. In generators the EMF is produced, so we find the direction of current. So in this we use the Fleming right hand rule. And the induced EMF is classified into two categories. One is statically induced EMF and another one is dynamically induced EMF. In statical, in the sense, so conductor is stationary and the magnetic field is moved. If this is the magnet, north pole, south pole, this is the, assume this is the conductor. So if the conductor is stationary, a magnet field is moved, then this is the statically induced EMF. In case of dynamically induced EMF, in the sense, conductor is moved and magnetic field is stationary. This is called dynamically induced EMF. The example for statically induced EMF is transformer, and the example of dynamically induced EMF example is generator. So now we see the each induced EMF separately. Now the dynamically induced EMF. So this is the magnetic flux or magnetic medium, and this is the conductor. In this the magnetic field is constant or fixed and the conductor is moved. So the flux density of this magnetic medium defined as B, and the effective length is effective length of the magnet is L. So for the one turn of flux linkages, that is psi, represented by 1 into L is the effective length into dx. Dx in the sense the conductor move distance, that is x. What is the variation we here represent as dx, and the flux density B. So here this is the flux and this is the conductor. So this is the conductor of position at a time of t, we can say. Now this is the motion at another t1, like. So if the angle between the two motion is this, if assume this is the total angle 90, so this is the theta in the sense this is the 90 minus theta. So what is the displacement distance? That is defined by theta, and here we take phi psi, that is equal to L, effective length, into distance moved dx into B for one turn of total flux linkage. Then the rate of change of flux linkage, that is d psi by dt, that is equal to L dx B divided by dt. So according to Faraday's laws of electromagnetic induction, so E, that is equal to rate of change of flux linking with the conductor. So we can write E, that is equal to BL dx by dt. Here we take dx is a distance, then dx by dt we can say velocity. So the induced EMF V, that is equal to BL into V, the unit is volts. Here the direction of EMF is obtained by applying the Fleming right hand rule. Let conductor moved with the same velocity with an inclined direction with an angle of theta to the direction of field, then the induced EMF, that is E, equal to BLV sin theta. Here the assumption is the angle between the conductor and the magnetic field is 90 degree. So right angle to the, so in this equation E is equal to BLV. Here the magnetic field is right angle to the conductor. If that's make some angles theta in the sense, we can write the induced EMF E, that is equal to BLV sin theta. So the EMF reduced by the amount of sin theta. And next one is statically induced EMF. So statically induced EMF has the two types. One is self-induced EMF and another one is mutually induced EMF. First one is self-induced EMF. self-induced EMF in the sense, if we give supply to the one coil, here the EMF sets around the coil, that is initially the flux set up on that coil. So this flux is called self-induced flux. And see this circuit, here the alternating source is given to the coil. So due to the supply, around the coil initially the flux is set up. This flux is called self-induced flux. Due to the flux linkages, nearby coil is also energized, so that here nearby coils also set up the magnetic flux. So this flux is called mutually. Due to this flux, the coil is induced, the EMF is created. This is called mutual induced EMF. So this mutual induced EMF we can measure this meter, that is induced voltage. So this is the self-induced EMF on that one coil. So nearby coil is energized and the flow of EMF is called mutually induced EMF. So now we completed the magnetic circuits, electrical circuits, and the interaction between the electrical and magnetic circuits, that is electromagnetic induction.